how we can calculate the relative atomic masses accurately. We can use a mass spectrometer to measure the mass of each isotope present in an element. But how is that? The mass spectrometer contains a heating chamber where the atoms of the element are first heated and vaporized. Then a heating filament that produces a high-energy electrons converts the vaporized sample into ions. The stream of ions is separated by deflection using a magnetic field according to their mass charge. The lighter ions travel faster to reach the detector at the end of the magnetic field tube. Then the heavier ions arrive afterward. The detector is connected to a computer that displays detector current, which is then correlated to the relative abundance of isotopes in percentage on the vertical axis and the mass to ion charge ratio on the horizontal axis. Let's look at this mass spectrum of neon. Neon has 3 isotopes, neon 20 with relative abundance equal to 90.9%, neon 21 with relative abundance equal to 0.3%, and neon 22 with relative abundance equal to 8.8%. The relative atomic mass of neon, ER, is equal to the sum of the 3 isotopes' relative abundance multiplied by their atomic mass, divided by 100. The relative atomic mass of neon is equal to 20 multiplied by 90.9 plus 21 multiplied by 0.3 plus 22 multiplied by 8.8 divided by 100 equal to 20.2. A high-resolution mass spectrometer often used to give a very accurate relative isotopic masses. For example, the high-resolution mass spectrometer can distinguish between sulfur dioxide and sulfur molecules, where the difference in the relative molecular masses are very small. Notice the relative molecular mass of sulfur dioxide is equal to 15.995 multiplied by 2 because we have 2 oxygen atoms plus 31.972 for sulfur equal to 63.962. On the other hand, the relative molecular mass of sulfur molecule is equal to 31.972 multiplied by 2 because we have 2 sulfur atoms. This is equal to 63.944. The high-resolution mass spectrometer can differentiate between sulfur dioxide and sulfur molecules that have a difference in the relative molecular mass between them equal to 0.018. This is how accurate it can be. Let's solve this example to understand the relative atomic mass. Look at the atomic mass spectrum of germanium. Write the isotopic formula for the heaviest isotope of germanium. Use the percentage abundance for each isotope to calculate the relative atomic mass of germanium. First, the isotopic formula for the heaviest isotope germanium 76 is germanium 76, or we can write it as 76 Ge. The relative atomic mass of germanium is equal to, we will multiply the mass to charge ratio by the abundance for each isotope. So 70 multiplied by 20.6 plus 72 multiplied by 27.4 plus 73 multiplied by 7.7 plus 74 multiplied by 36.7 plus 76 multiplied by 7.6, and we will divide them all by 100. This will give us that the relative atomic mass of germanium is equal to 72.703. You can see that this number is close to the number presented in the periodic table for germanium relative atomic mass. Our next topic will be about the mole and the Avogadro constant.